This first panel we've called Airspace, which is a way of bringing together people, as Lindsay says, which is from different disciplines and different backgrounds, but talking about similar themes. So we will have Andrew Turner talking about the INCOMPASS project and its field campaign, Nerea Calvillo, Airscapes in the Making, and Victoria Watson on Yves Klein's paintings of thunderclouds. And I'll just introduce our first speaker. Dr. Andrew Turner, after studying physics at Oxford, completed his PhD at the University of Reading in 2006 on the subject of the relationship between the monsoon and the El Niño Southern Oscillation as a means for predicting a season's monsoon rains. In particular, he looked at how the systematic errors in the ocean surface could limit the effectiveness of forecasts. Since then, he's continued to study climate variability and change in the Asian monsoon region and is leading collaborations with the Met Office and internationally, including the INCOMPASS project, a ground and air-based field campaign as part of joint work between the UK Natural Environment Research Council and India's Ministry of Earth Sciences. Andrew.
Okay, thank you. Can you hear me? Yeah. Okay, so title at the top is the kind of soundbite short title. Title at the bottom wasn't such a good one to put in the program because it's quite long. This talk is going to be about understanding and predicting the monsoon in weather and climate models, thinking about the current state of knowledge and why we need to have observational campaigns. And that's what this thing INCOMPASS was. It was an observational field campaign in India last year where we took a load of measurements of the monsoon. I'm just going to move this down a bit. Okay, can you still hear me? Yeah. Okay, so I'll take you through what is a monsoon. And we had some interesting discussions yesterday about perhaps how people perceive what a monsoon is. But I'll give you a definition from a scientific perspective about a monsoon. And then I'll talk about the ability that we have at the moment to simulate monsoons in the Asian monsoon region. And that's really what motivates us to try and work very hard on improving the forecasting models that we have for weather and for climate. I'll talk very briefly about some of the ways in which the forecasting models that we use for weather and climate work. And there's a process there, or a methodology called parameterization that I'll mention. And finally, we'll get on to probably the most exciting bit of the talk really is about this field campaign that we did last summer in India. And we actually took a research aircraft from the UK and flew it to India and did a lot of research flights and so on. Okay, so before we get on to rainfall, which is what most people think about as the monsoon, we'll just think about what drives it at a very, very fundamental level. And it's much more complex than this, but this is the basic idea, and it's about contrasts in temperature at the surface of the planet. So these two graphs are showing the surface temperature of the sea and of the land in spring times. So at the top we've got springtime for the southern hemisphere, and at the bottom we've got the late spring for the northern hemisphere. And what happens in springtime? You know, we've got the sun overhead over, let's say, the Tropic of Cancer in the northern hemisphere. And we skipped ahead there. We tend to find that the Sahara Desert, parts of Saudi Arabia, northern India, they warm up very quickly and they reach very hot temperatures, much more so than the nearby ocean. Okay, so we have what's called a temperature gradient. So if you look here in this region of India, you get this temperature gradient between India and further south, right? Elsewhere in the northern hemisphere, this also happens for West Africa. And this is not just a phenomenon that happens in the northern hemisphere, this is something that happens in the southern hemisphere also. So we think also about the Australian monsoon, and coming into towards the summertime of the southern hemisphere, northern Australia has become much warmer than its surrounding oceans. So what is the effect of that on the wind or the circulation of the atmosphere? The effect of that is that if we just think about India, essentially this hot air, in very simple terms, is going to rise. So that hot air is rising. And in terms of physics, to conserve mass, that air that's risen up has to be replaced at the surface by air from somewhere else. So air is rising up here over India, and then it's being drawn in at the surface from further south over the ocean. Okay? And the whole way that this works is that the air is going to carry with it moisture that it's picked up, that it's been evaporated from the Indian Ocean. It's going to take it to India, and eventually it's going to rain. And that probably will become a bit more clear on the next couple of slides. So that was looking at the surface temperatures. Now if we switch to looking at the winter and the summer season, and I live in the northern hemisphere, so that's the way I think. The top one is the winter. That's December, January, February. The bottom one is the summer, June, July, August. You can see that for the Asian monsoon region, the average direction of the winds has changed dramatically between winter and summer. So just to mention that these are the winds at approximately a height of 1.5 kilometers. As meteorologists, we tend to think in terms, we don't tend to think in heights of kilometers, we tend to think in pressure heights. So you might know that the surface has a pressure of about 1,000 millibars, and this is actually at a pressure height of 850 millibars. It's a lower pressure, but it's about 1.5 kilometers high in the atmosphere. So this really represents the circulation of the winds in the lower part of the atmosphere. And between the winter and the summer, you can see that the winds have changed direction dramatically. They're now going towards these very high temperatures, and what these winds are going to be doing is carrying that moisture from across the Indian Ocean. So for those of you who know a bit about India and are studying it in the context of this project, you may often hear this referred to as the southwest monsoon because these winds are coming from the southwest. Similarly, in the wintertime, there is a northeast monsoon for some parts of India, Sri Lanka and so on, and that's because these winds are coming from the northeast. But fundamentally, for West Africa, for China, because these winds are coming across the land, they're just going to be picking up dry air. There's no source of moisture to rain. Okay? So on the next slide, what I'm going to do is show you the same seasons, but a picture of rainfall, and we'll see how that changes between the winter season and the summer season. Okay, so there we are. So this is a rainfall product from a combination of satellite measurements and rain gauge measurements. And again, it's averaged over the June, July, August season here, and the units are millimeters per day. So this is millimeters per day of rainfall on this quite a coarse resolution product. But what you can see is that from having virtually no rain on average in the winter season, India suddenly gets a very large amount of rain in the summer. So this is what people generally think of as the monsoon. It's this seasonal change in the rain. But as scientists, actually, what the monsoon really is a seasonal change in the winds, a seasonal change in the prevailing winds. And in fact, the word monsoon is derived from an Arabic word, morzam, which means season. So that's where that comes from. So one can imagine then that for society in India, and similarly for West Africa and so on, society is going to be very strongly tied to the fact that there's this very strong seasonality in the rainfall. So just to think about that in terms of some numbers, 80% of India's rainfall occurs during the summer monsoon. So just between June, July, August, September, that's 80% of the annual rainfall. If you want a number, that's around about, on average, 850 millimeters per year, so that's 85 centimeters, so maybe that's high. That's the average accumulation over all of India in the summer. I looked up London on Google last night. I don't know how accurate that number is, but London gets about 600 millimeters annually rainfall through the whole year. And I guess another important point to point out is that this is not the same everywhere over the country. Some parts get much more than that, maybe 2 meters, 3 meters of rain. Other parts get much less, much drier parts of the country. So the economy is strongly tied to the monsoon, so is agriculture. Historic droughts, such as one that was quite large in 2002. In 2002, the monsoon rains were about 20% below normal. There was a significant loss in GDP that year because of the loss of agricultural output. So this is an animation. Again, the monsoon is not something that suddenly switches on the 1st of June and happens the same everywhere. This is a chart from the Indian Met Office, just showing the typical day at which the monsoon starts in different parts of the country. And classically, we think of 1st of June in Kerala, the southwestern state, as the kind of, that's the onset everyone talks about, when the rains start and first hit the southwest of India. And then that onset line moves north, and it sort of hits the border with Pakistan round about the middle of July. So it's taken 6 weeks for the monsoon rains to get across the whole country, on average. Okay. And when the monsoon retreats at the end of September into October, this tends to go back in the reverse direction. And so what that means is if you're in the south of the country or the southwest, your monsoon season is actually much longer than if you're up in the northwest part of India, in Gujarat, in Rajasthan, and so on. Just to mention, because it's quite important for the physics and the dynamics of the situation, mountains are actually very important for monsoons. This is just a map of typical heights that's been smoothed somewhat. You can see there above India, you've got the Tibetan Plateau. So for years and years, people thought of the Tibetan Plateau as a real thing that's helping to drive the strength of the Indian monsoon, because it actually heats the atmosphere to a very deep level. But more recently, there's been important work looking at the impact of the Himalayas on the monsoon. And the Himalayas are actually quite important in separating the moist air that's coming from the ocean from drier air that might be coming in from across Eurasia, the Eurasian continent. Okay, so we're leading into perhaps the most, certainly the most difficult to explain slides of the talk, from my perspective. But the point is there's only a few key messages to take from this. So the next couple of slides, they're going to talk about data from models, from climate models. So these are from the coupled model intercomparison projects. Okay, so that's referred to in these slides as CMIP. And the CMIPs are the big multinational centers. These are the models, the climate models that they make, and they put towards the IPCC reports. So these are the models that are used to do climate predictions for the end of the 21st century, and so on. And the most recent set of these models is called the CMIP-5 models, and they contributed to the IPCC fifth assessment report. So lots of modeling centers have run these models, they've made these future projections, and then the IPCC report is reviewing the results and saying, well, what's going to happen to the monsoon in the future, or to the sea ice in the Arctic, and so on. On these slides, I might also show an earlier set of models, which were called CMIP-3 models, and they were the models used in the fourth IPCC report. Okay? So, okay, here we are. Some pictures of rainfall. So, at the top, on the left, this is a picture of observed rainfall for the monsoon summer, for June, July, and August in this case. You can see there's a lot of rain, so in some cases there's 12, 15, 18 millimeters per day over the west coast of India. Again, over northeast India, Bangladesh, a lot of rain, over the Bay of Bengal, a lot of rain. That's what the observations look like. Here we've got two different climate models. This is a French climate model. This is a Japanese climate model. And there's nothing to do with the future here, right? These are just trying to show, they're trying to simulate the 20th century. So what do these models, how well do they do at simulating the monsoon in the 20th century? And you can see that this pattern of rainfall in both cases has some resemblance to the observations, but it's not brilliant. This one, I think we would argue, looks rather better than this one. So that's just thinking about the pattern. We can also, obviously, we can look at a difference between the two. So we can look at a difference between the rainfall in one of these models and in the observations, okay? And that's what we're showing on the right. We're just doing this diagram minus this diagram. Very simple. And what you can see here is we've got a scale that goes from, you won't be able to read, -5 to +5. So what it's saying is that this model has around about 4 millimeters per day, too little rainfall in the 20th century for India. And this model, this has a somewhat different pattern. Parts of it look drier, parts of it look wetter. So the point here is just to say that the models that we use to simulate climate have errors, and we want to understand why that is. And they have a range of different errors, but there are some similarities. So on the next slide, what I've done is, you'll see a similar picture to this and this, but I've actually taken the average of all of the models that are in this database. So about 25 models went into the diagram. So that's what's shown at the top. So this is the average of about 25 different models trying to simulate the monsoon of the 20th century. And this is the difference to observations. So there's a consistent message in those models that they're all too dry at simulating the monsoon. And as a scientist, this really motivates us to try and understand why there is this error. So it's something we need to understand. And here's a depressing thought, okay? So the models at the top are the CMIP5 models. So these are the ones that went into the most recent IPCC report. About 10 years earlier is the models that went into the previous IPCC report. You can see that it doesn't look like there's been much improvement there. The errors are actually quite similar. There have been subtle improvements, which my colleague Ken Sperber goes into great detail about, but the main message here is that there's a lot of work still to be done to improve the situation. Not sure how well this one will come out, especially at the back, but this is just showing the same picture for the wind. And we know from what I told you at the beginning that the winds, and understanding how the winds change, are vitally important for the monsoon rains. So this is just the average of all of the models. And I'll draw, and you can believe me that the winds are doing this sort of C shape, which is about right. They've got these winds coming from the southwest, hitting India. If you compare it to an observed estimate of the winds, then again, believe me, or come and look at the slide later, you can see that these winds are much too weak. So the fact that the winds are too weak is what we call consistent with the fact that the rainfall is also too dry over India. Those things are intimately related. So there's a lot of work to be done. And again, CMIP3, the same idea, the older models. Okay, so I thought I'd show this purely to give you a more, or just think about in another way that this seasonality of the rainfall is important. So this is showing, we've just taken a box and drawn it around India and we've averaged the rainfall in that box, and we're just plotting it out month by month, okay? And the most important line on this graph is the solid black line here, which is from some observations. So you can see this really is a monsoon country. For the country as a whole, it's getting its rainfall in the summer months and virtually none at all in the winter months. And the other lines are just six models from this model database. And they happen to be the best 6 models that my colleague found. And you can see some of those are actually quite bad. So if those are the best 6 models, what do the other ones look like? Okay, so the need for parameterization, so AKA why we might need better observations. So this is a very, very, very brief introduction into how weather and climate models work. So if you imagine dividing your globe up into a grid of latitude and longitude lines, so a bit like a globe actually, but with far finer lines on it. What these models do is they solve the equations of motion for the atmosphere on that grid. So at each grid square they solve those equations. And not only the equations of motion, but also they think about thermodynamics, they think about cloud processes and so on. So this is an example of the Met Office's, UK Met Office's climate model from around about 2005. This is when I was just sort of finishing my PhD. And this is another version of their model from about 5 years later. And we've just chosen UK because everyone's familiar with the UK, obviously. And to give you an idea of, at that time, how many kind of boxes would cover the UK at the resolutions they were using. So the sort of size of one of these grid squares at that time, 3.75 by 2.5 degrees, or in kilometres, round about 270 kilometres. And in the 5 years hence, they have essentially doubled the resolution. Okay, so they've now got boxes that are half as big in both directions, 135 kilometres. And this is not something that's just for the UK. It's a global model. It's trying to predict the climate of the future, and they have to have these squares covering the whole Earth. So we've doubled the resolution of this model. What do you think is a consequence of that? There is potentially twice as much data. I would actually say it's 4 times as much data because you've doubled it in both directions. Yeah. So that's important. The other thing that's important is the cost. So if you have the same supercomputer system and you double the resolution in both directions, so it's 2 times 2, which is 4, that's 4 times as expensive to run. Okay? And another detail on here is that actually between that time they'd also divided the atmosphere up into a greater number of layers. They've also doubled the resolution in the vertical direction. So that becomes 8 times what it was before, 8 times as expensive, assuming it's the same computer system. So that's an issue, okay? Okay, so just bear those scales in mind. So 270 kilometers, 135 kilometers, but that was 7 years ago. The latest Met Office climate model that we typically use is about 70 kilometers, so it's doubled in resolution again. So that's a global climate model. You will most be familiar with the Met Office because they actually do weather prediction. And it's a very different thing that we're trying to do. Okay? If we're trying to predict the climate at the end of the 21st century, say, we need to run our model for several decades, or centuries even, if we're going beyond that. And so it needs to be at a quarter resolution. If we're doing a weather forecast, we're only going to run maybe 5 days ahead, 1 week ahead. So we can afford to be much more profligate. We can afford to ramp up that resolution. So one of the models that the Met Office use for weather forecasting globally has a resolution of about 17 kilometers. So that's for their global forecast model. Now for the UK it's different, you know, they can do also higher resolution ones of just the UK. That's a different thing. But if you just keep this in mind, that even their global weather forecasting model has a resolution of about 17 kilometers. So here's one of their grid squares, 17 kilometers. Now in the tropics, in somewhere like India, the typical individual clouds that might be involved in what we call tropical convection, they might only be a few kilometers wide. So even at this resolution, we're not able to represent these explicitly. So what they have to use as a methodology is something called parameterization. And there's a great deal of work done onto this. It's about giving a statistical representation of the average picture of what clouds will look like within one of these squares based on the information that they know at those scales. Okay? So that's what parameterization is. And why have I even mentioned this at all? This is why we think there are errors in those climate models. Okay? So we want to try and either make better parameterizations, or ultimately, in the future, we could make models that have a much, much higher resolution. But that's very, very expensive. So the only way to make better parameterizations is to take more and more observations in order to do better programming, to understand the physics of what's going on with things like the formation of clouds over somewhere like India. Okay, so that motivates INCOMPASS, which is a big field campaign that we did last year in India. So just as a nice starting picture, I thought, well, let's think about what the air is doing as it approaches India. And this is a map showing a few different things, but I only want to focus on two bits. One is all the grey areas. That's just bits where there are mountains, and I've just decided on a height of something like 600 meters here. So that's showing that there's some important mountains to the north. There's obviously the Himalayas, Tibet, but also there's these mountains on the west coast that we call the Western Ghats of India. So if we imagine our monsoon air flowing from the west, this is picking up moisture from the Indian Ocean. As some of it hits that mountains, it's going to start to rain. So that's something that motivates us. We're wanting to understand, well, why? What are the processes going on there? Secondly, as the air carries on, goes over the Bay of Bengal, it picks up some more air that's moist. You know, it's picking it up from the ocean. This is moist air. And as it gets back into northern India, as it hits the coast, as it perhaps goes up into Bangladesh, it can again force rainfall. The other feature on this map, this comes from a data set from the UN, from the Food and Agriculture Organization. And I'm not sure how much I trust it, but it's apparently showing the percentage of land area that is equipped for irrigation purposes. And these bright green colours that's 75 to 100% of the land area. And if you've ever been to northern India, certainly around the Ganges Basin, there's an awful lot of canals, there's a lot of fields that have groundwater pumps and all of these sorts of things. So there's a lot of water just being used to cover the land surface and to provide moisture for agriculture. So another thing that motivates us in this field campaign is trying to understand, well, is this air also going to pick up some of this moist air from the surface? Okay, so as the wind flows back over northern India, is it going to pick up some of that moisture? And there have been studies elsewhere in the world, chiefly in Africa, that show that at the boundaries between soils that are dry and soils that are wet, you can help develop storms in those places. So this is something we really want to understand. You know, is this a source of those errors that we get in our models? Okay, another thing that motivates this INCOMPASS project is just how the monsoon changes and some of the contrasts in space as the monsoon changes. So this is just showing rainfall, in this case in the middle of May, in the middle of June, middle of July. It's averaged over many years of data, and it's just to give you an idea, again, reiterate that it's not just a homogeneous blob of rainfall over the whole country. There are important spatial contrasts here. So chiefly over the southern part of peninsular India, so where Bangalore is here somewhere, there's this big contrast from west to east. Heavy rainfall on the Western Ghats, much drier over the southeast India, Chennai, at that time of year. We want to know more about that contrast. What does the atmosphere look like as let's say we were to fly through it? What does it look like? Then in northern India, you can see that there's also this contrast. As you go in from the coast, the rainfall really drops off. And that contrast is there very early, before the monsoon starts properly. It's there during the monsoon and into the middle of the monsoon, but it's evolving. So we really want to think about why and can we better model that? Can we better forecast it? This is showing the same periods. It's just showing what we call the frequency of rainfall. On how many days do we expect it to rain? And it's expressed as a percentage. So this is, the blue colours at the top are about 95%. So in 1 in 5, is that right? 19 out of 20 days, you'd expect it to be raining in some of these places on the west coast. The redder places up in Rajasthan, even during the middle of July, it still might be only raining on 1 in 10 days or 1 in 20 days. Not very often. Okay, so the last sort of section of the talk, just thinking about the field campaign that we did and taking new measurements to try and understand this. So we want to understand these different contrasts in chiefly 2 different locations. One is across the south of India, a strong contrast here, and the other is across the north of the country, and we want to know how that's changing as time goes on. And the main way that we did this, and there's some pictures on the next slide to make it more interesting, we used the UK Natural Environment Research Council's atmospheric research aircraft. And to give you an idea about this, it can hold about 18 scientists, obviously a couple of pilots, and believe it or not, you also need a cabin crew member because they have to ensure everyone at the right time has their seatbelts on, and also to bring out the gin and tonic and so on. Sadly not. And what we can do with this aircraft is that we can measure what's called in situ things, so things at the location of the aircraft. So it's got probes. We can measure the temperature of the air, the humidity. It's not something that is so interesting to me personally, but there are other scientists on the plane who can look at the chemical constituents of the air, the aerosol product in the air, the pollution. But in addition to those in situ measurements, it can also give you what's called remote sensing. So it has radar and something called a LiDAR, which is a laser-based radar, essentially. It uses light to reflect off surfaces and give you a picture of the atmosphere below the aircraft. So we can get things like the cloud structure from those instruments. And this thing has a typical range of about 4.5 hours flying time. So here is a picture of it. It's quite big. There is actually an airline that operates out of City Airport that uses an equivalent sort of plane. It takes about 80 passengers if it didn't have scientific equipment in it. This is what it looks like inside. There's a couple of seats at different workstations, lots of instruments. These pump out an incredible amount of heat, which is fine if you're working in the UK. If you're working in India, it's a big, big problem. And we had to do a lot of logistical thinking to get around that. This picture is not from our field campaign, but it's just to give you an idea of how low this thing can fly. So we were doing flights, in some cases over the ocean, down to 100 feet for up to an hour at a time. and you just see the waves going past. You see little fishing boats. It's really quite something. I'll just very briefly, it's a very short video, just click that. This is just an example. That's the cockpit. There's a view from the window. This is what it looks like inside. Lots of different instruments, pipes, people using computers, looking at measurements live as they're happening all the time. So really quite an involved process. There were some instruments there. They're not missiles. They're sort of instruments that hang from the winds. There were a lot of organizations involved. We co-led it with the Indian Institute of Science in Bangalore. So we did, over the course of June and July last year, we did 22 flights in the locations indicating here. So we were running from 2 airports, one of which was Lucknow in northern India. The other was from the old Bangalore airport in southern India. So we managed, I think, if you go back to my motivations, we managed to capture these different contrasts in the monsoon. And the data that we've got from these flights, we're going to study for the next few years and really try and improve our forecasting models. This is an example from a flight. I won't dwell on it because there's no need to, but just to highlight the typical height profiles that we would do during a flight. So here we've taken off, landing here, but often what we would do is we would do the first portion of the flight at high levels, so really at the top of the troposphere, that sort of height, or maybe about 22,000 feet, something like that. And then we would return on roughly the same route at low levels. And when we're flying over land, assuming there's no mountains in the way, we can fly consistently at about an hour at about 600 feet, which is really, really low. You can't go down to 100 like you can over the sea. And a problem then actually is that because you're much nearer the surface, you start warming up again, and the instruments are pumping out heat, and it gets very, very hot, and it's unpleasant actually. So that would be a very typical thing for our flight. So in this case, we flew from the airport somewhere out to the west and back, but the way we'd done it was we came out at a high level, returned at a low level, and that's to sample different parts of the atmosphere. We also had a section of ground instrumentation, and I've made you aware of the interesting bits about the irrigation and so on. The top is just showing a map of something called FluxNet. It's a measure of different instruments that measure interesting things at the surface. So the heat and the moisture that comes up from the surface of the Earth. And as you can see, there seem to be lots of these measurements in North America and in Europe, but in a lot of the tropics in India, they're missing. So another thing we did in this project was to install some new instruments. We did about 8 of these over the country at lots of locations in different types of zones to improve those measurements. Here's some example sites. I won't dwell on what we're measuring, but the important thing is we're looking at the temperature and the moisture that's coming up from the surface. So there's an example tower growing in an agricultural field, and this is going to provide us with really important measurements for the future. Another thing to point out, I suppose, is that these pictures look quite idyllic, but I can tell you that it is just roastingly hot. For someone who's used to living in Britain, you know, this is. I remember one day we were here; it was in the early 40s, and you know, it was just too hot. Another thing we were launching a lot was these weather balloons, and these really give us vital information, not just at one point, but about each level of the atmosphere. And another challenge, actually, when you go to India, is the health and safety issue. And when I first arrived at this site, this gas bottle, which was about this high, was just kind of standing there in the middle of a concrete area. And I said, look, you know, you've got to strap that up because otherwise that's going to fall over and that'll break someone's leg, so that's not good. But this is an example of the sorts of measurements those things gives you. This is the surface. Right up there is the top of the troposphere, and these give you really detailed information about the temperature and the moisture that's in the atmosphere. And right at the end now, this is what the rainfall looked like over all of India during that 2016 season. So we're going to be studying in depth what has happened in the atmosphere as we've gone from these wet periods into dry periods, and vice versa. Very last slide. We want to really push the boundaries of modelling. These are two examples of models at different resolutions for India, and they're showing rainfall on one particular day last year. This is that global model that runs at 17-kilometre resolution. This is a model running at 4-kilometre resolution, giving you much finer detail. The other important thing is that both of these diagrams are actually at the same time of day, and the way that these models represent rainfall during the day is very different. Okay? This one is more realistic in terms of when the heaviest rainfall is happening in the daytime. So I'll leave it there, really. This is what we're hoping to use our observations in to try and improve these models at both of these different scales. And thank you very much.
Thank you very much, Andrew. That was a wonderful introduction into the monsoon and how it's being followed and measured and tracked and projected.